So the next colligative property and the last colligative property is osmotic pressure. So in earlier session we discussed about the relative lowering of vapor pressure, elevation in the boiling point, depression in the freezing point, and the last one is the osmotic pressure. So here osmosis means the spontaneous flow of solvent from the dilute solution to concentrated solution through a semi-permeable membrane until the two solutions becomes a equal concentration is known as the osmosis process. So for example, here you can take the one big container. So this big container is having the two portions. That two portions are separated by the semi-permeable membrane. Assume that this is the semi-permeable membrane. Now in this you get the compartment A and this is the compartment B. So in compartment A you can take the only the pure solvent you can take. Now here you can take the solution. So here the spontaneous flow of the solvent molecule into the solution through this semi-permeable membrane is known as the osmosis process. And not only this solvent and solution, here you can take the dilute solutions, and here you can take the concentrated solutions. Here also the spontaneous flow of solvent molecules from dilute solution to concentrated solution through the semi-permeable membrane is known as the osmosis process. So while this transferring of solvent molecule from the dilute solution to concentrated solution, this process should occurs until these two solutions becomes equal concentration. That is known as the osmosis process. Now here we discuss the semi-permeable membrane. So here the membrane which allows only solvent molecules, which can allows only solvent molecules but not the solute molecules, is known as the semi-permeable membrane. And this semi-permeable membranes are different types are there. For example, natural semi-permeable membrane is a pig bladder. So pig bladder and membrane of cells, and even a cellophane paper, parchment paper, parchment paper, and even so these are the some organic semi permeable membranes. Even one example for the inorganic membrane, that is the calcium phosphate. So calcium phosphate is the one example for the inorganic semi permeable membrane. Semi permeable membrane means what? The membrane which allows the only solvent molecules but not the solute molecules is known as the semi-permeable membrane. And these are the some examples for the semi-permeable membrane. And next one is the osmotic pressure. And earlier we discussed the osmosis process and semi-permeable membrane. Now you can take this in a closed container. Okay. Now here solution is there. Okay, we can take the one more diagram. Now this one is the semi-permeable membrane, and here you can take the only pure solvent, and here you can take the solution. So osmotic pressure means the pressure is required or the pressure is applied. For example, here piston is there. This is the piston. So through this piston we have to apply the external force or external pressure. So the external pressure is required just to stop the inflow of solvent molecules into this solution is known as the osmotic pressure. So usually the solvent molecules will flow from a dilute solution to concentrated solution, or from solvent to solution side. But whenever this applied pressure is greater, at the time this applied pressure can prevents the flow of these solvent molecules into this solution is known as the osmotic pressure. So the pressure is required or pressure applied on the solution just to prevent the flow of solvent molecules is known as the osmotic pressure. So according to one half, these dilute solutions or behaves like a ideal gases, and you know that ideal gases equation PV is equal to nRT. That ideal gases should follows the all the Boyles laws, that is the Boyles law, Charles law, Avogadro's law, and Gay-Lussac's law, Dalton's law of partial pressures. So here also the dilute solutions can follows the Boyles law and Charles law. And here want of applied the Boyle's law and Charles law. Okay, Boyle's law and Charles law for the dilute solutions. So in ideal gas, the pressure is directly proportional to its volume. And here want to have factor for the Boyle's law of dilute solutions you can take. For what? Dilute solutions. So osmotic pressure we have to represent with a pi. So osmotic pressure is directly proportional to concentration, and this concentration is inversely proportional to volume. When volume is more, concentration is less. When volume is less, concentration is more. Now pi is in place of concentration, you can take the 1 by v. Then we can get a pi v is equal to k, means by removing this proportionality we can get the k, means in a Boyle's law for gases we can take the pv is equal to k. Same in place of p we are taking the pi. That's it. And you can take this the equation 1. Now you can apply for the Charles law. Charles law, osmotic pressure is directly proportional to temperature. Then pi is equal to k into T. Then k is equal to what? Pi by T. Now you can take this is the equation 2. Now from equation 1 and 2, then osmotic pressure is directly proportional to the temperature and inversely proportional to what? Volume. Now if you remove this proportionality we can get the one constant, that is the s t v. Okay, then pi is equal to c s t you can take, because here s t is there, and 1 by volume nothing but what? C only. Then we can get the pi is equal to CST, and here S is equal to solution constant. So for 1 mole of dilute solution, for 1 mole of dilute solution, so pi v is equal to RT. So pi v is equal to what? RT. For n mole of solution, here only you can take, for n moles of a solution, then pi v is equal to nRT. Remember these equations. And here n is equal to what? Number of moles. So that number of moles equation, we know that Wb is equal to what? Weight of solute, and Mb is equal to molecular weight of solute, weight of the solute and molecular weight of the solute. So then N is equal to what? Wb by Mb. Now we can substitute this equation in this one. So pi V is equal to Wb by Mb into RT. Then from this equation, Mb is equal to what? Wb RT by pi. Wb RT by P. This is the equation is useful to calculate the molecular weight of the solute by using the osmotic pressure. And we will see the isotonic solutions, hypotonic solutions, and applications of mm, osmosis process. Okay. Now see isotonic solutions. So here we know that iso means what? Same. Iso means same. Isotonic solution means the solutions which are having the same osmotic pressure is known as the isotonic solutions. Okay, see the solutions which are having same osmotic pressure is known as what? Isotonic solutions is known as isotonic solutions. So examples, you can take the RBC cells, means red blood cells, or isotonic with a saline. Here saline nothing but 0.9% normality of sodium chloride is nothing but the saline. So usually whenever the human beings are suffers with any illness, so immediately the doctors will suggest to keep salines, because whenever the persons are feeling somewhat illness, at the time in the body or in blood vessels the pressure should be more. To control that, the doctors will suggest the saline. Okay, means here RBC cells and saline are the examples for isotonic solutions. It indicates RBC cells and salines are having the same osmotic pressure. So that only, so whenever if any person is suffering with vomiting sessions, at the time whatever the food and whatever the liquid, if that person is taking, immediately it will come out, because RBC cells pressure is the different, and what are the food materials or liquids that person is taking, that osmotic pressure is different. So at that time, how much osmotic pressure is there for the RBC cells, the same osmotic pressure containing liquid we have to take, so that only they will suggest the saline. And here one more thing, so whenever this RBC cells, if we keep more than the 0.9% normality of sodium chloride, so at the time what will happen? For example, no, here we can take this one is the RBC cells. Okay, so this RBC cells is having a 10 atmospheric, for example you can take the only 1 atmospheric pressure. Now these RBC cells, if we keep in more than 0.9 percentage of normality sodium chloride, what will happen? Here this is the one solution, and this is the another solution. Now this solution is having the more concentration and this one is having the less concentration. At that time what will happen? Whatever the solvent molecules are there or liquid molecules are present in RBC cells, those solvent molecules will flow from RBC cells into this concentrated solution, means more than the 0.9% normality of sodium chloride. So at that time this all these RBC cells will shrink and the RBC cells becomes less. Okay, and if you keep these RBC cells in a less concentration, for example less than 0.9% normality of sodium chloride, what happens? This is the solution is having less concentration and RBC cells are having more concentration, so that the solvent molecules will flow from this less than 0.9% normality sodium chloride into the RBC cells. So whatever the solvent molecules enter into the RBC, that RBC cells can take up these solvent molecules and becomes large, so it indicates those can will be swell. So at what condition the RBC cells will swell? When RBC cells are kept in less concentration than the 0.9 normality, and RBC cells will shrink when or when those cells are kept in more than 0.9% normality of sodium chloride. So means RBC and saline, these two are having the same concentration, or sorry, same osmotic pressure, so that these two are the isotonic solutions. And means here I will write, so when RBC cells with a 0.9% normality, those are the isotonic. So when RBC cells with a less than 0.9% normality of NaCl, what happens? RBC cells will shrink as well. So RBC cells will swell. And when RBC cells with more than more than 0.9% normality of sodium chloride, so what happened? RBC cells will shrinks, meaning the size becomes less, and here the size becomes large. And the next one is the hypotonic solutions. Hypo means less, hyper means more. So hypotonic solution means the solutions which are having less osmotic pressure than the other solution is known as the hypotonic solutions. Okay, the solutions which are having less osmotic pressure than the other solutions. And hyper means large or more. So the solutions, so which are having more osmotic pressure, more osmotic pressure than the other solutions is known as the hypertonic solutions. For example, you can take a plant cells. Okay, plant cells. So if we keep these plant cells in a hypotonic solutions, what happens? The plant cell becomes swell or shrinks. The plant cell will swell. And if we keep these plant cells in hypertonic solutions, What happens? The plant cell becomes shrinks and the size of the plant cell becomes very less. Okay, and this is about the isotonic solutions, hypotonic solutions, and hypertonic solutions. Now we will see the applications of this osmotic pressure, osmosis, and isotonic solutions. So for a raw mango is there. So usually in this starting of the summer season, in most of the homes they will prepare the mango pickles. So before preparing the mango pickles, they will cut the raw mangoes into small pieces and they will keep in a salt solution. Otherwise they will pour somewhat salt in that mango pickle pieces. After 3 or 4 days, if you observe, some amount of water will come in that solution. So means from where we are getting that water? That water we are getting from the mango pickle pieces only. Means whatever the water molecules or solvent molecules are present in the mango pieces, raw mango pieces, that solvent molecules will come out through the osmosis process. Okay, and even so in a flower market, uh, the merchant will pour some water on the flowers. So continuously he will sprinkles the water on wilted flowers. Okay, so whenever he is sprinkling some water on that wilted flowers, the wilted flowers can take up the water and they become somewhat shiny. And even the plants can take the water from the ground is also depends upon the osmosis process. Okay, and next one, one more important one is the edema. So edema is the one type of medical disease. So edema means people taking lot of salt and salty food, those are more experienced with the retention in tissue cells or muscles is known as the edema. Okay, so edema means what? Edema means people people taking a lot of salt or salty food experience with a retention in a in tissues cells is known as the edema. Okay, so actually here I didn't return the applications of osmosis and osmotic pressure. So in textbook they mention clearly that you can note it in the notes. And next one is the reverse osmosis. So it is very important for the 1 mark questions and even 2 marks also they will ask reverse osmosis. So reverse osmosis means the flow of solvent molecules, the flow of solvent molecules from solution into the solvent through semi permeable membrane. Semi permeable membrane when applied pressure is greater than osmotic pressure is known as the reverse osmosis. So reverse osmosis means what? The flow of solvent molecules from solution into the solvent through semi-permeable membrane when applied pressure is greater than the osmotic pressure. And one applications of this reverse osmosis, desalination of sea water. So usually sea water is unfit for the drinking, but by using of this reverse osmosis process, we can convert the unfit water into the drinking water. This is about the osmosis, reverse osmosis, and osmotic pressure. And one more important point is, so if a solution 1 and 2 are having osmotic pressures, osmotic pressures pi 1 and pi 2, and volume is v1 and v2, then resultant osmotic pressure is, osmotic pressure equation, pi is equal to pi 1 v1 plus pi 2 v2 by v1 plus v2. So this the equation is useful when two osmotic pressures which contains different volumes at the time. To find out the resultant osmotic pressure, we can use this equation. Okay.